Okay, so now Dr. Kern and I are going to look at one last example that we just cooked up to try and explain um, the difference between average velocity and instantaneous velocity. And so in this scenario, I guess I have a mango tree next door to my house, and so I'm going to throw a rock at the mango tree to try and knock down one of the mangoes. So I'm going to throw the rock with an initial velocity of 32 feet per second. And because the force due to gravity is negative 32 feet per second squared, this is a negative 16 there for the acceleration due to gravity, right? Is that correct, Dr. Kern? Close enough? Or?
That is correct. And don't worry about if you don't know why that's true from a physics viewpoint. You'll learn eventually, but much later in the course.
Okay. And then I'm 6 feet tall, so I'm assuming that I'm throwing from an initial height of 6 feet. So then this black curve is the plot of the height of the rock that I threw as a function of time. So at 1 second, it's at 22 feet, and it must hit the mango or miss the mango and then come back down. And after 2 seconds, it's back at 6 feet. And then finally, after 2.173 seconds, it would hit the ground. And so if we wanted to calculate the average velocity of the rock as a function of height there, I guess, over the time interval from 0 to 2, we would get an average velocity of 0 because it went up and then it came down, and so then the change in Lee Memorial helicopter going overhead. The change in the overall change in height over those 2 seconds is 0 there, but obviously it had to have some velocity at some point, right? Because I threw it up with an initial velocity of 32 feet per second. So what's going on here? Well, this is f of a, which is 0, plus 2. So that's f of 2 minus f of 0 all over h. That gives us 6 minus 6 is 0. So we had no run there. But then again, what would be, if I wanted to figure out what is the instantaneous velocity at, let's say, a equals 0, what could I do? Well, I could make my h values get closer to 0. And I guess if I make h equals to 1, then I would get an average velocity of 16. So that would be over the first second, the average velocity is 16 feet per second. That looks better.
Yeah, it looks a bit better. One thing you might want to, if you remember from the video when we talked about the definition of the derivative, that blue line is actually a secant line. So even though we're talking about velocities here, in fact, it really is the same problem as when you're talking about secant lines and a tangent line.
Yeah, so this is one of the first applications of the derivative, right? Is you're calculating the instantaneous velocity by taking the limit as h goes to 0 of the difference quotient, but you're using a velocity function instead of just a cooked up function, I guess.
Right.
And I wanted to make this go to 0. So I guess you can see that if I plug in 0.001, then the average velocity over the time interval from 0 to 0.001 is 31.98, which is really close to what we claimed the initial velocity was, which was 32. I guess because we've done this example too many times, we can just look at the equation and say, oh yeah, initial velocity is 32 feet per second. Any other closing comments? Or?
No, that looks pretty good. Just keep in mind that these are going to work all the same way. And again, this is a nice example. It comes out, if you took the actual limit, it would come out to a very nice number. And would tell you the instantaneous velocity, which is the same thing as the slope of that tangent line, the blue line that you see there. But remember, a lot of times it doesn't end up being a nice number, so you really have to make sure you take the limit each time.
That's good advice.